Okay, so let's start. Um, in the previous class, we looked at an algorithm for solving unconstrained optimization problems, unconstrained convex optimization problems, called gradient descent, and another version of gradient descent, which was the method of steepest descent. Effectively, the method of steepest descent is, you can think of it as a way of choosing the step size in gradient descent. So that's just a variation. So now we have an algorithmic technique for solving smooth convex optimization, unconstrained smooth convex optimization problems. Right? And our goal is to be able to solve not just unconstrained optimization problems, but also constrained optimization problems. And towards that, we'll see properties of convex sets and convex functions. And we'll see that, of course, there's the one problem is actually how do you solve a convex optimization problem, but the other problem is how do you formulate a problem as a convex optimization problem. And we'll see that through an example, right? So in the previous class, I introduced this example of maximum weight matching. So you can think of so the most abstract version of the problem is the following. You have a bipartite graph which consists of n vertices on the left and n vertices on the right. Right. So I have n vertices. So I have n vertices on the left and n vertices on the right. For every pair of vertices from the left to the right, there is a so-called preference or a weight. Right. So if I label these vertices as 1, 2, 3, 1, 2, 3, then for every pair of vertices I have some preference. Let me call it W11, W12, W13, and so on. So in general, the preference or the weight for the edge connecting the ith left vertex with the jth right vertex is Wij. Okay. So this is a given graph. The goal is to pair these vertices together. Right? So for every vertex on the left, I want to associate exactly one vertex on the right. And similarly, every vertex on the right should be paired with exactly one vertex on the left. That's why it's called a perfect matching. So the goal is to match these vertices together such that the total weight is the maximum. So for example, this is one example of a matching. So maybe these two vertices are paired up, these two vertices are paired, and these two vertices are paired, right? So 1, 3, 2, 1, and 3, 2, this corresponds to a perfect match. So formally speaking, what is a perfect matching? A perfect matching is just a subgraph of this particular graph such that every vertex has degree exactly equal to 1. Okay, it's a subgraph of the bipartite graph. A perfect matching is a subgraph of this complete bipartite graph such that each vertex has degree exactly 1. Another way of thinking about this perfect matching is that it's essentially just a permutation, right? So for every vertex on the left, so it's essentially a bijective mapping from the set of left vertices to the set of right vertices. So, and the weight of any perfect matching is just sum over all possible edges in the perfect matching. So the sum of the edge weights in any given perfect matching is the weight of that particular perfect matching. And we want to choose a perfect matching that gives you the maximum weight. Okay, any questions so far? Is the problem clear? Okay, so as you can see, this looks like a combinatorial problem. There are n factorial possible perfect matchings, and you can find the weight for each perfect matching and find the one which is the maximum. Unfortunately, this has computational complexity order n factorial. The question is, can we come up with a simpler, more efficient algorithm to do this? But to see how we can simplify this, let's try to formulate this as an optimization problem, as a mathematical optimization problem. Right? In particular, we'll try to formulate it as a constrained optimization problem. So what do we want to maximize? Effectively, what we want to maximize is, okay, so even before that, I want a set of variables. So what is given to me is the following. So what is given is the set of all Wij for every pair ij, I comma j. Right? I can represent this as a matrix. Right? Which is in general an n by n matrix. Right? So first, in order to formulate any optimization problem, I need to identify the set of variables. So I'll define the following set of variables. So for every I comma j, I'll associate it with xi comma j.
So this table is the adjacency matrix of
So it's the weight. So the matrix. It's essentially the matrix of weights. Because each Wij can be a real number. It can be an arbitrary real number. And we're assuming that for every pair, I have some weight associated with it. It could be 0. Which one? So W is not necessarily a symmetric matrix. So let's take a concrete example. Let's take a 2 by 2 example. I have 1, 2, 1, 2, right? So remember, it's a bipartite graph. Okay, so let's create some weights, 0.2 and 0.7, 0.3. Okay, so what would the W matrix look like? So what is W11? It is 1. W12 is 0.2. W21 is 0.7 and W22 is 0.3. So this would be an example of a weight matrix. So in general, for an n by n matrix, I have a weight matrix. Okay, so again, let's take this specific example. What would be the matching that gives you the maximum weight?
1, 1.
Which one? 1, 1 and 2, 2. Right? Again, it has to be a perfect matching. So every vertex on the left should be connected to exactly one vertex on the right, and every vertex on the right should be connected to exactly one vertex on the left. It should correspond to a permutation. So there are only two possible matchings. One matching is 1, 1, 2, 2. The other matching is 1, 2, 2, 1. What is the weight for 1, 1, 2, 2? It is 1.3. What is the weight for 1, 2, 2, 1? It is 0.9. So the maximum weight matching would be, in fact, 1, 1, 2, 2. I can't really select 1, 1, 2, 1 because that would not correspond to a perfect match. Okay, is that clear? All right. So in order to represent a matching, a perfect matching, I will define certain variables. So I'll define xij to be the set of all variables. So xij can take values either 0 or 1, which means that the ith, so xij basically represents whether the ith left vertex is connected to the jth right vertex or not. Okay, so let me so xij equal to 1 if I and j are connected in the perfect matching and 0 otherwise. Okay, I'll define these to be my variables. Okay, so for every I comma j, I have an xij. So suppose I have a perfect matching, then what would be the objective function? F of, let me say x, yeah. Okay, so you mean to say that x should be a permutation matrix, correct? So overall possible permutation matrices. So, but what is the objective function? Suppose I give you xij. Correct. So this would effectively be summation overall I comma j wij xij. That would be the objective. But of course, I can't choose these xij's arbitrarily. It should correspond to a perfect matching. So I could potentially say it is the sum. So I want to maximize this quantity over all possible permutation matrices x. For a given x, this is the objective function. Okay. So the problem is basically to find maximum of f of x over all x, a permutation matrix. Is that okay? But I'll rewrite this slightly differently. I want to explicitly write down all the constraints that need to be satisfied, and I'll write it in a specific way. So let me say that this is also equal to the maximum of f of x, which is summation overall ij wij xij. What I want to do is express the constraint that it should be a permutation matrix in terms of linear constraints. Okay, so can you give me a set of linear constraints that imposes the condition that it should be a permutation matrix? Correct. And so in every row I should have exactly 1 1, and in every column I should have exactly 1 1. Right, that essentially corresponds to a permutation matrix. So I will write this in the following way. So summation overall j equal to 1 to n xij should be equal to 1 for all I Similarly, for all j in 1, 2, 3 up to n, summation I equal to 1 to n xij should be equal to 1, and xij should be either 0 or 1. Correct. So I'm representing it in terms of arbitrary binary variables here, right? So this defines permutation matrix, right? That's what I'm just rewriting it in a particular fashion. There's a specific reason why I'm doing this, right? Because in the end I want to come up with a better algorithm than just searching over all possible permutation matrices. Right now, what I have is a combinatorial optimization problem, right? And I could write, in fact, I have this particular set of constraints. I could instead also say that xij should be a positive integer, or at least a non-negative integer. Of course, these two, it's superfluous because these two constraints impose that xij should be either 0 or 1. But anyway, let me write it down in that particular way. Xij is the set, belongs to the set of all non-negative integers. Okay. Correct. Every permutation matrix would correspond to perfect matching and vice versa. Right. So again, I've done nothing over here. I've just rewritten the optimization problem in this particular fashion. All right. What I'll do next is try to do what is called a relaxation of this particular problem. What I have over here is a discrete optimization problem, because the variables can only take positive integer values, in fact, just binary values. A relaxation, a convex relaxation of this is where I just relax these integer constraints. Instead of saying that it should be a positive integer, I just impose that xij should be greater than or equal to 0 for all I comma j. Right. So what would the relaxation of this particular problem be? Find so it's a maximum over all I comma j wij xij, such that for all I still have the summation to be equal to 1. So I'm now maximizing. You can think of this as an optimization problem where the variables correspond to a matrix, an n by n matrix. So every row should sum to 1, every column should sum to 1. But now I'll just say that each xij should be greater than or equal to 0. Can be any arbitrary real number, just greater than or equal to 0. That was in the original problem, right? Now I'm defining a new problem. Which one? I'm not saying that. So this is a new problem that I'm trying to define. Okay. Right now I'm not saying that this will give the same answer as the previous problem. My actual problem is, of course, this. So this is the actual maximum weight matching problem. This is what I call a relaxation of the maximum weight matching problem. Correct.
But how we can allow
It can't be, because I want all of these constraints to be satisfied, right? So in fact, it cannot take, the constraint set does not permit you to take 2. It will take only 0 or 1 if all of these constraints have to be satisfied. but I'm just writing it as a set of positive integers. You're right. I could that what I should actually write is xij being in either 0 or 1. But both these constraint sets are the same. It doesn't make a difference. Okay. And the reason why I'm writing it in this particular way is because you can now see the connection between this and this. So here it could be an arbitrary positive integer. In this case, it's an arbitrary positive real number. Sorry, a non-negative real number. Correct? In fact, even here, each xij can take values between 0 and 1. Okay? So this is what I call the relaxed problem. It's a new optimization problem. Okay? I'm not saying that the solution to this is the same as the solution to the other one. All right? So, but now if you see the set of both the objective function and the constraints, they're all linear. So this is what is called a linear program. So it's a specific version of a constrained optimization problem where both the objective function and all of the constraints are linear. So in general, a general linear program essentially takes the form maximum or minimum of A transpose X subject to the constraints that some matrix A times X is greater than or equal to B, where this greater than or equal to is an element wise greater than or equal to. Okay. Any questions? So this is the general formulation of a linear program, and for the maximum weight matching problem, this particular version is what I'll call the linear programming relaxation. Now it may seem that I've only complicated the problem, right? Originally I had a discrete optimization problem where my search space was finite. But now I've come up with a continuous parameter optimization problem where the solution space is infinite. But as it turns out, this is a simpler, easier version to solve. All right. Whereas the older problem had complexity n factorial, this will have a complexity that is just polynomial. And in fact, I'll be able to solve this for a very large number of variables very efficiently. Okay. So now let's suppose that we have to solve this particular problem. Now I could of course sort of first develop the theory of linear programming and so on, but now let's see a black box technique to solve this optimization problem. I won't give you an algorithm, but we'll see a Python package that will help us solve convex optimization problems. And later on, we'll try to open the black box and see how the algorithms actually work. Okay. But let's first see how we can use these tools. So in this course, we'll use a Python package called CVXPy. Alright, so there's a lot of documentation for this. We won't go through everything in CVXPy. We just use it as and when required. But as long as you're comfortable with Python programming, this is not very difficult. It's quite similar to NumPy. So a bit of the syntax is the same. There is plenty of documentation, including how do you use the various commands. There are a lot of examples, a lot of practice problems, and so on and so forth. Okay. So for now, we'll just use this CVXPy to solve this maximum weight matching problem, or the LP relaxation of the maximum weight matching problem. All right. So I'll first define import numpy as LP. Okay, so now I define the problem itself. Right. So I have to first define the problem. I'll set n equal to, let's try to solve the toy version of the problem that we had. Let's take n equal to 2, and now I need a matrix, the weights. So let me take W to be equal to np dot array of, can you tell me what the values were? What is 1 1? 1. Yep. 0.7, 0.2, 0.3. Okay. So this fully specifies the problem. Good. So now I need to define the variables for my optimization problem, and I can do so using the following method. So I define the variables as cp dot variable. I want to define an n by n matrix. So again, it's similar to numpy n comma n. So this defines a variable consisting of, or it defines a matrix of variables, n by n matrix of variables. Now I should define my constraints, correct? So what are all the constraints that I have? So you write all the constraints as an array, a comma separated with each constraint separated by commas. I have the constraint that each xij should be greater than or equal to 0. Right? That's one set of constraints. In fact, I can just say greater than or equal to 0. That's it. So this takes care. This is an element wise greater than or equal to. Okay. What is our next constraint? Every row should sum to 1 and every column should sum to 1. I have cp dot sum x comma axis equal to 0. So every row should sum to 1. This should be equal to 1. And cp dot sum x axis equal to 1 equal to 1. That's okay. So it takes care of all of these. I could, of course, in principle, I should really say ones of that particular dimension, but this is fine. Just like numpy. All right. So I've defined the variable. I've defined the constraints on the variables. Now I need to define the objective function. So the objective is, it's a maximization problem. Right? And what is it? It's basically, I take the element wise product of W with X and sum it up. Right? Again, it's fairly simple. CP dot sum everything. So remember, I'm not, so these are not numpy arrays. So W is not a numpy array, correct? it is an object, it's a CVXPy object. All right, so I'll have to use cp.sum, not np.sum. So cp.sum of cp.multiply w and x. Okay, so this ensures that I take the element-wise product, and this ensures that I take the sum of all the elements. And this says that I'm trying to maximize this particular function. Okay, great. Now this is the objective. Now you have to formally define the problem, which basically says problem equal to cp dot problem of objective constraints. That's it. So this fully defines the problem, and now I want to solve. So solution equal to cp dot prob dot solve. So what exactly is happening over here? So each of these are, so you define the constraints in terms of some inequality or equality constraints, and you define the objective function. When I call problem.solve, in the background, CVXPy uses a number of convex optimization solvers, so numerical optimization solvers, depending on what kind of a problem this is. So in this case, it is clever enough to identify this as a linear optimization, it's as a linear programming problem, and uses a suitable solver. In fact, it's quite robust in the sense that you can also ask it to use a specific solver to solve your optimization problem. There are a number of solvers that you can use, but there's some default solver that is going to be currently used. So just warning that it's using some default solver, but it's going to be start using something else instead. So it has in principle solved this problem. Let's see what the result is. So this is the maximum weight that is going to output. But for the toy problem, what was the maximum weight? It was 1.3, right? And let's see what the solution is. Right? I mean, these two entries are almost equal to 0. I mean, after all, it's using a numerical solver, so small, you have to allow that small tolerance, but it's actually giving me a perfect matching. Let me try to look at a different problem. Okay, let me just set this to be W equal to of n comma n. Let me take a 3 by 3 matrix and I'll print W. Okay, so here it's a little difficult to identify what the perfect weight matching should be, but let's say I somehow fix the perfect weight matching. Okay, so let's say W, give me a matching. Yeah, 1 1 2 2 3 3. So let's say W1 comma 1 equal to or equal to 1. right? So this would in fact, the actual maximum weight matching would in fact be the identity matching, because all of the other entries are less than or equal to 1. Okay, you're convinced? Fine. So let's again use the solver. What should the value of the max weight matching be? 3, right? And in fact, that's what I get. Right. So this is very close to 1, 0.999. This is also 0.999. This is also 0.999. In fact, you'll see that no matter how I change this, even if I just randomly generate a matrix, I run this, I will always end up with a perfect match. So maybe it's not so clear. Yeah, so this is very close to so it's 0.999, 0.999, and 0.999. In fact, there's a slightly better way to visualize this. I can just print. So the yellows essentially represent 1 and the dark blue represents a 0. So you can see that it's a 0, 1, 0, 1, 0, 0, 0, 0, 1. In fact, let's take a bigger example. Let's take a 10 by 10 example, let's say. I again generate a random matrix. I run the algorithm and let's say I print this is what the matrix would look like. It's not a very useful visualization, but the lighter the value is, the higher the corresponding entry is, and the darker values correspond to values that are close to 0. Okay, so you can see it's all over the place, but let's look at the solution, right? The value of x, the optimized value of x, that turns out to be a perfect match, right? You can see in every row there is exactly one yellow box, and in every column there is exactly one yellow box. So this in fact corresponds to, yeah? Can you speak up?
Quantizing from the previous image to the current image.
It's not a quantization. So what I originally plotted was the matrix of weights, right? So, but this gives you the matching or the final value of x. Yeah, in fact, it gives you exactly 1. Yeah, or close to it, 0.999. So right now it's just a solver, right? It's a black box. So it's actually trying to solve this particular optimization problem. It is solving this particular optimization problem and outputting the solution for this optimization problem.
Taking block where it is having the highest weight and it is spread.
No.
Like it is giving it a top.
What do you mean block?
Like we have weights WIG, like in a specific row,
Mhm.
it is giving us the weight WI where it is maximum. Like,
That's not what it is doing.
the college you won't be getting like you are saying that
what you're trying to get at, I think, is a greedy procedure, right? It is not a greedy procedure. We'll see how to solve these optimization problems later, but it is not a greedy procedure. It is actually trying to almost exactly solve this particular optimization. The only subtle point that I'm trying to make is that this optimization problem is different from this optimization problem, because here there was an explicit restriction that each of the entries in Xij should be 0 or 1. Whereas here I'm relaxing that particular constraint. It could be any real number between 0 and 1. However, when I actually perform this numerical optimization, when I try to solve the relaxed problem, it turns out that every single time I run it, I always end up with a valid permutation matrix. Right? That should be something surprising. In fact, I can take much larger problems. I can take 100 by 100 matrix. Let me not print W. I solve this. Remember, if I had to brute force this, I had to search through all possible perfect matchings, then the computational complexity would be like 100 factorial. But let's see how long this takes. Done. Right? And this is what the output is. It may not be immediately obvious, but this will correspond to a permutation matrix. Right? So that's surprising. I did some kind of a relaxation, but somehow it turns out that the solution is the same as the solution that I was looking for. Yes. Correct.
It is supposed to be
I know.
should be 0 and 1.
It's surprising that I'm getting 0 or 1 because the optimization problem I'm solving is different, right? So here, numerically, I am not solving the maximum weight matching problem, but rather the relaxation of the maximum weight matching problem. So here, which allows values between 0 and 1. In principle, when I solve for this, I could end up with an X that gives me fractional values. Right? That's perfectly possible. And in fact, I've hidden one small aspect of this. It turns out that there are certain ways of choosing these Wijs for which you can get fractional values as the optimal solutions. Okay, but almost always you will get integer solutions. You'll get but even then there will be integer solutions. But yeah, we'll see that in just a little bit. So in fact, it turns out that the solution to this is equal to the solution to this. Exactly. Okay. I have to be a little more careful over here. When this problem has a unique solution, the solution to this is equal to the solution to this. If this problem has multiple solutions, in the sense that there is more than one X that gives me the maximum value, then at least one of the solutions will be the solution to this. Okay. Any questions? Okay. So
the constraints of the CPU, the CHQS where X, can you create a constraint of X is 0?
You mean X equal?
Yeah, X belongs, we made the relaxation.
Correct.
X is the positive here.
Correct.
Can you create a specific constraint that X can be only 0?
It cannot. You cannot. You cannot. Yeah. Because the solver that I'm using is a convex optimization solver, which means that or whatever constraints, whatever functions that I input must necessarily be convex. If I don't, then in fact, if I feed a non-convex constraint over here, it will just output an error. It will not even try to solve. Okay, so for example, if I say that I want to maximize, let's say x square, or suppose I want to do, maximization of x square, which is not a where you're trying to maximize a convex function, it will just output an error. Okay, so this is very specific in what kind of optimization problems it can solve. Okay. Any other questions? Okay. So now let's try to see, at least intuitively try to see why the relaxation gives me the same solution as the original problem. And of course, how do you solve the relaxation? For now, we won't focus on how do you solve this particular optimization problem, but we'll take it as a given that if I have a convex optimization problem, I know how to solve it efficiently. So if I'm able to pose my problem as a convex optimization problem, where the function is convex, the constraints are also convex, then there's some procedure to find the optimal solution numerically. But the original problem that I had over here was non-convex. In fact, it was a discrete optimization problem. So let's see the specific case, why in this specific case the two turn out to be the same. In general, it's not the same. Okay. So to do so, let's try to think about the linear programming problem itself. Okay. So let us think of each of these constraints. Okay, so take a general linear program. So take any one single constraint. What does a constraint look like? It is some AI transpose X greater than or equal to BI. So this is one such constraint. What kind of a set does this define? So let's think about this in 2 dimensions. I take a 2-dimensional vector A, and I want to know what is the set of all X such that A transpose X is greater than or equal to B. So it will be a region above a line or below a line, depending on what the value of B is. Correct? So first, let's look at the following constraint. This is what is called a hyperplane. Right? So the set of all X in Rn such that A transpose X equal to B, this is a hyperplane. And what can you say about this? What kind of a set is this? I know, but it is convex. It's also a subspace. It's a subspace of Rn, right? Because it corresponds to the right null space of a particular 1 by n matrix. And what is the dimension of this particular subspace? Yeah. Why? So let me call this H. What is the dimension of H? Okay, it's n minus 1. Why?
Dimensions.
Mhm.
N would be on N
That's a definition, right? What you're basically saying, but
N minus 1 linearly
can you be like, what result are you using over here to say that the dimension is n minus 1?
we can have that N minus 1 basis for this. So the dimension of this.
Why can you get a
Because there
dimension?
exists a vector which is linearly defined, like E equal to A transpose X. So we can be written as a linear combination of vectors. So you can't find any
Okay.
linearly independent.
So we're basically just using the rank nullity theorem, right? So I can rewrite this A transpose X equal to B in the following way. So this is the same as A transpose times X minus some X0. So this will have at least one solution. Let's call it X0. Take any vector X0. So it is A transpose times X minus, so it is a set of all X such that A transpose X minus X0 equal to 0. Right? Now this is a vector space, so I should be a little more careful. So H in itself is not a vector space. It's a shift of a vector space. So this so the set of all X minus X0, that forms a subspace, right? So I can write this as set of all, say, Y plus X0 such that A transpose Y equal to 0. So the set of all Y for which A transpose Y equal to 0 forms a vector subspace, right? And again, just by the rank nullity theorem, so A is a matrix of rank equal to 1. So the set of all Y satisfying A transpose Y equal to 0 just forms the right null space of this particular matrix, and therefore the null space would have dimension n minus 1. So this set, the set of all Y such that A transpose Y equal to 0 is a subspace of dimension n minus 1. So we'll say that the dimension of this hyperplane is also equal to n minus 1. It's effectively nothing but a shift of this particular vector subspace. Now if I had to visualize this in 2 dimensions, I give you a matrix, a vector A, A1, A2, and I want to plot let's say I have this. Right? What does the vector A represent? Yeah. The intercept
slope is
in 2 dimensions. Let's try to think about this in 2 dimensions. What would A represent? Yeah.
The point of so A will be V1 minus
A will be V1 minus V2. Okay, how do you get that? Okay, I'm talking about the vector A. So geometrically, how is A related to any point X on the hyperplane? Perpendicular, right? So in fact, what does A correspond to? The normal vector, right? So in fact, the direction of A just corresponds to the direction of the normal. Okay. And what does x naught correspond to? It's just a shift, right? So in principle, I could take any particular x naught on this particular line. So this would be my x naught. So geometrically, the way to think about this hyperplane is, so mathematically, this is equal to the set of all x such that A transpose x equal to B, but A just corresponds to the normal vector. This is true in any dimension. So even in higher dimensions, let's say 3 dimensions, the hyperplane will just correspond to a plane, right? And A would be nothing but the normal vector. So A would be the normal vector, and B, loosely speaking, corresponds to the shift from 0. Okay, so this is a hyperplane, right, which defines an equality constraint. So set of all x such that A transpose x is equal to B. Now, an inequality constraint of this particular form, AI transpose x is greater than or equal to BI, would correspond to either the region above the hyperplane or the region below the hyperplane. And we call each of these regions a half space. Each of these regions are half spaces. So hyperplane effectively partitions Rn into 2 half spaces. One region, so to speak, above the hyperplane and the other region below the hyperplane. So each linear inequality constraint corresponds to a half space. Okay, that's what we've established so far. Now, what we have is not just one linear inequality constraint, but a bunch of linear inequality constraints. All of them have to be satisfied. What would this set look like? The set of all x which satisfies, let's try to look at a general set of inequality constraints. How A times x is greater than or equal to B. Correct. So when I say that all of these constraints have to be satisfied, it's effectively an intersection of half spaces. Right? So here, in fact, there are, if A is an m by n matrix, then there are m linear constraints. Right? And this corresponds to an intersection of m half spaces. So I have one half space, maybe this is another hyperplane, and this is potentially a third hyperplane, a fourth hyperplane, and a fifth hyperplane. Right? In each of these cases, maybe I also have another, something like this. Corresponding to each linear inequality, I have whatever, maybe the first linear inequality defines this particular half space, the second defines this particular half space, the third corresponds to this particular half space, and so on. So I'm taking a finite intersection of half spaces. What do you think geometrically what would this constraint set look like? Okay, it's convex, but something more familiar, more elementary. Like, just think about it in 2 dimensions. Okay, in 2 dimensions, each half space is basically a region below or above a certain line, correct? And I'm taking an intersection of such regions, of many such regions. What would the corresponding geometric figure look like? It will be convex, but it'll look like a polygon, right? Assuming, of course, it's bounded. In general, it need not be bounded, but if it is bounded, it's going to look like a polygon. Correct? You all agree? So, if the set of constraints is something that is bounded, then it's a polygon. In general, so any finite intersection of half spaces is what is called a polytope or a polyhedron. Right? So polyhedron is any set that is an intersection of finitely many half spaces. Okay. This might be unbounded also. For example, if we just take one half space, then that's obviously an unbounded set, but we'll still call it a polyhedron. We'll use the terminology of polytope if it is also bounded. Now, sometimes people use these two terms interchangeably. Some people say that a polyhedron is bounded, whereas a polytope is unbounded. But we'll try to use the following notation that or terminology that a polyhedron could potentially be unbounded, may be bounded or unbounded, but a polytope is always bounded. The set is empty. That's still a polyhedron. It's also a polytope because it's bounded. Right. So in particular, if the set of constraints is inconsistent with each other, then you could end up with an empty set. But it's still, that's fine. All right. So now let's try to visualize let me take a general linear function, 2x plus 3y. Okay, I just plot this function. It's going to be some plane, right, with a certain slope. So I get something like this. Right? Um, so recall that our objective function in a linear program is linear, right? So in general, it will look something like a plane. Correct. So let me view this from the top. It looks something like this. In fact, I'll view it in the direction of decreasing or increasing gradient. So as I move towards the north, the function value keeps increasing. As I move towards the south, the function value keeps decreasing. Correct? So if I have any sort of constraint set, any bounded set, where would the maximum be achieved? At the top, at the northernmost point. Do you agree? Is that something that is intuitive? Well, somewhere at the top. Again, I'm not making a rigorous statement over here. Correct? Should be at some boundary point, but whatever the boundary point is, it's going to be somewhere at the top. That's all. That's the only point that I'm trying to make over here. All right. So now let's go back here. Suppose I'm given an arbitrary linear program. Okay. And suppose I take this picture and
Sir,
yes.
is the area of that one the area dependent
Which one? So this is some linear function. Okay.
is it constructible x
No, this is my objective function. Okay, you can think of this as the objective function. My goal is to maximize this objective function subject to some set of constraints. Okay. So in general, my set of constraints will be some subset of Rn. In this case, some subset of R2. Right? And the maximum will be achieved at some point, doesn't matter where. But the only point I'm trying to make here is that suppose I view this function from the top and I also superimpose the set of constraints, then sort of the northernmost point in this set of constraints would correspond to the maximum, would be the maximizer. Okay. So this is what the objective function looks like, right? So the more orange it is, the higher the function value, the more blue it is, the lower the function value. Now let's look at the set of constraints. The set of constraints would correspond to some, I have a set of linear, it's a linear program. So each constraint would correspond to some particular half space. So the set of all constraints would give me some kind of a polygon, assuming that it is bounded. All right. Now visually, if you see, at what point do you think the maximum would be achieved? It would be at this particular point, right? It would be at this particular point. So at least intuitively, no matter how I choose this set of linear constraints, the maximum would always be achieved at some vertex. Now, even if I had a different set of constraints, like so in principle, I could have a set of constraints for which the maximum is not unique, right? Maybe this is the constraint set. The constraint set is the set of all points in this polygon. The maximum would be achieved by any point on this particular line. But even then, the maximum is also achieved at some vertex, right? I don't have to look beyond vertices to find the maximum. So that's a special property of linear programs in particular. The maximum is always achieved at a vertex. So even though it's a continuous parameter optimization problem, effectively the number of solutions, the number of possible solutions is still finite. It's equal to the number of vertices. That doesn't mean that you can solve it very efficiently, right? Because it's possible that the number of vertices is very, very large. But if you are able to identify what the vertices are, then all you have to do is just search over all possible vertices. In fact, the first algorithms to solve linear programs effectively use this intuition that you only need to search along the vertices, and more so, you don't need to search along any arbitrary vertex. The intuition for the first linear program, first efficient linear program, was the following. You just start with an arbitrary vertex, all right? Suppose I start with this particular vertex. There are a number of edges incident on that particular vertex. Along each edge, you can basically try to find in which direction the function value increases. And there's no point in going in the direction of decreasing function value if your goal is to maximize the function. So you keep moving along those edges where the function value is the maximum, it keeps increasing the highest value, and you keep moving until you reach the vertex wherein in all directions the function value only decreases. Right? I'm just heuristically describing this algorithm. You can prove that this is optimal and is also efficient. Okay. So the main point here is that linear programs can be solved very efficiently. There's a separate set of algorithms that do this. But the more important point is that given any linear program, for any linear program, the optimum is reached at a vertex. Okay. Any questions so far? Sorry. Correct. So right now what we have is a geometric intuitive description. We'll define what a vertex is more formally later on. But effectively, when you take the intersection of half spaces, so any point that does not correspond to an edge would be a vertex. Okay, not a face or not an edge. We'll define it later on using what are called supporting hyperplanes and so on. All right. But at least in 2 and 3 dimensions, we have an intuitive understanding of what a vertex is. Right? And at least here, I would say that the optimum is always reached at a vertex. We can also define it for higher dimensions, which we will do later. Okay. So now let's go back to the original problem that we had, or the 2 problems that we defined. So first was the original maximum weight matching problem and the linear programming relaxation. So now we know that if I look at this linear program, the maximum is reached at some vertex of this constraint set. Okay. So if it is possible to show that the set of all points that satisfy this corresponds to all the vertices of this, then we are done. Then the 2 optimization problems are effectively equivalent. But in general, for linear programming relaxations of general integer programs, the vertex set for this polytope could potentially be different from the set of all points that satisfy these constraints. But in this specific case, wherein I have this set of constraints, it turns out that the set of all vertices of this exactly correspond to the set of permutation matrices. So recall that we have the following set of constraints. The set of all matrices X such that Xij is greater than or equal to 0 for all I comma j, summation over all I Xij equal to 1, summation over all j Xij equal to 1. So the set of all matrices that satisfy these properties are what are called doubly stochastic matrices. Why is it doubly stochastic? What we're saying is that every entry is greater than or equal to 0. Every row sums to 1, which means that every row is a PMF. It's a valid probability mass function. And every column is also a valid PMF. So it's a valid probability mass function. So both rows and columns have to be stochastic. That's why it's called a doubly stochastic matrix. Okay. The exact details of this particular problem are not important. The point that I'm trying to make here is that by understanding the geometry of these sets, we know how to formulate our optimization problems cleverly. Remember that originally I had a very complicated looking problem. It was an integer program where the overall computational complexity was n factorial. But now I reduced it to a linear program where all of a sudden I could solve an optimization problem with 100 by 100 matrices very efficiently in just less than 1 second. Right? And that is really the power of convex optimization. You can have very large, in fact, integer programs, but these relaxations can be solved very, very efficiently, provided you know how to make these relaxations cleverly. If I didn't make it cleverly, then potentially I could have ended up with some other solution and only an approximate solution. But now I have a very efficient way of coming up with the exact solution very efficiently. Right? So in case you are interested, there's something called the the Birkhoff von Neumann theorem, which says that so this set of doubly stochastic matrices, it forms a polytope, right? The Birkhoff von Neumann theorem essentially says that the vertices of this polytope are precisely the set of all permutation matrices. So every permutation matrix is obviously a vertex of this polytope, but as it turns out, there are no fractional vertices. So if I call this Pn, right? So just to summarize, we looked at the maximum weight matching problem, which was originally an integer program. We looked at the relaxation of this. We took the linear programming relaxation, which we saw that we could solve very efficiently, right? And we used some specific geometric properties of these linear programs to show that the relaxation, I mean, I have not proved it over here, but one can give a formal proof to show that the two are essentially the same. Both the integer program as well as the linear program yield the same solution, right? This was something that was observed maybe only the last couple of decades, not much before that. So this gives you a very efficient way to solve at least this class of max weight matching problem. All right. So in the next few classes, we'll explore more such convex sets and study their properties. All right. We'll extend the notion of the hyperplane to what are called affine sets, and we'll try to see how all of these work in higher dimensions. Right. Let's stop here.